Okay. So wait for based on how we see it, it will be chaos on there, right? Okay. The whole group stuff? No, just yeah. I guess we can start. So, welcome everybody to this week's Software Live seminar. It's our pleasure to have Boris Köpf from Azure Research or Microsoft Research, I'm not sure which one you prefer, here with us. Boris is a alumnus from ETH Zurich. He did his PhD here, and I'd like to first say welcome back to one of your homes. And he has been a tenured professor in India, and also he has been doing great research in the past several years in Microsoft Research. The main focus is on tracking information flow in microarchitecture and machine learning systems. So we're excited to hear what modern undetected microarchitecture means as well. So yeah.
Thank you very much. Thank you very much for the introduction and for being such a lovely host. So I've been in Zurich now for 2 days, 3 days, and it's really great to be back. And thanks everybody for coming. So the title that was announced is slightly different from this one. The title was about automatic detection of microarchitectural leaks, but I will also talk a lot about modeling microarchitectural leaks because this is the key component, as you will see, for detecting them later. This is work that we have been doing. This is work that we have been doing over the last 3-4 years with a bunch of collaborators from Azure Research and the broader industry and academia. And let me point out Alexei for 2 reasons. First of all, he's the lead developer behind the second part of what I will present in our talk. And second, because he's also here, so you can grab him if you have questions afterwards. So the problem of side channels begins with sharing. Sharing is, if I show that in the UK, then people would, like, as a reflex, continue with caring. But sharing is also called to cloud economics. So if you want to offer a competitive cloud service, then you will want to maximize the use of your available hardware. And that means there's a strong incentive to share hardware components, memory, network, caches across tenants. So that's good. Sharing is good for cloud economics. Sharing is bad for security because if one tenant uses a resource, that usage pattern somehow depends on secrets, and another tenant can observe that usage pattern, then the first tenant is broadcasting secrets all over the cloud, and we want to prevent that. So there's this trade-off between the benefits of sharing and the downsides, mostly in terms of security of sharing, and we need to address that. But one important aspect to this is that, like any radical solution, oh, let's just not share, comes with a very, very high cost. So we need to be very mindful how do we navigate that space. Yeah, and these attacks where you inadvertently, or the effect of inadvertently distributing information through shared resources, they're called side channels. The most prominent one is the cache side channel, and I mean a very simple example that I guess most of you have seen a gazillion of times. It's just like you have two memory accesses to an array. The array is not cached prior to accessing it, and the latency of the second access will tell you something about the relationship between I and J, namely whether they map to the same contiguous 64 bytes, like the same cache line. If they do, then the second one is a cache hit. If not, then the second one is a cache miss, and you can tell the difference because there's a latency difference of a few hundred clock cycles depending on the cache. So it's observable, and just yes. So the low latency reveals a relationship of I and J. And then there's a speculation, another performance enhancing feature comes into play, then the situation becomes even more complex. So here, this is a bounce check bypass, Spectre and Meltdown, the most iconic example. So here you have an array access, and first you do a bounce check. But if the CPU cannot evaluate the guard, because stuff is in memory, then it will predict where to go. So it can predict to execute this code, even though we're out of bounds. Then we would speculatively read out of bounds. And then with the second memory access, where this secret is used as an index, we would leak this into the cache. And after the execution, you could just like scan through the array B, see on which position you get a cache hit, and then use the effect of this first cache side channel to just determine what you just read out of bounds. So this is Spectre v1. I assume most of you have seen this. Right. So how do we detect those side channels? Well, first of all, I mean, Spectre v1 popped up 2018, 2017. And since that, there was almost every month some new microarchitectural optimization has been exploited, some new variant of this attack has come out, and it keeps us busy until this day. So how do you detect those? Well, usually through manual labor and creativity. So you need to read documents, manuals, patterns, papers. You get an idea of what's going on under the hood in the CPU, and then you make a hypothesis and confirm that by manual experimentation. And this is a very slow and ad hoc process. And most importantly, stuff that's undocumented is even harder to find. So if stuff is not documented in a pattern or a manual, then good luck with finding those leaks. So it's slow, it's ad hoc. Once we've detected them, so how do we make sure that we're not running into the same issues over and over again? Well, we document them. So for example, there's websites by Intel where all of the known leaks are documented, and usually those documentations happen in informal and ambiguous language. So these two text snippets describe the cache side channel and the bounce check bypass that you've seen previously. And if you read them and don't know what's going on, but good luck with understanding what's going on. So it's ambiguous, it's incomplete. And finally, so now we found them, we've documented them, how do we mitigate them? Well, we mitigate them usually on a per attack basis. So a new attack comes up, people need to react, and then either you fix it in the microcode of the CPU, or you fix it in the hypervisor or the guest OS, or maybe in your crypto library, sometimes in multiple places. And then you do that all the time, focused on one specific attack. Obviously, there may be gaps, but maybe just as important, there may be redundancies, because something that you have fixed in the OS that you later on fix in microcode of new CPU generations, well, now you've got a patch upon a patch upon a patch, and you pay the performance cost of this. So there's redundancies, there's gaps, and both are problematic in their own ways. So overall, it's not a great situation, and it's not a great foundation for building secure systems on top of it. So we don't like this. We're wondering what can we do. So when Spectre happened in 2018, there were a couple of proposals coming out on asking for a new ISA. So instruction set architecture describes the functional behavior of the CPU, but it doesn't describe timing behavior, for example. And it abstracts from the timing behavior deliberately, and in this way it kind of hides all the microarchitectural implementation, and it does not like essentially it hides those vulnerabilities. So people have asked for a new hardware-software contract. Some radical approaches were like, oh, we need to change and extend the ISA to be able to effectively control timing of the CPU from the software side. And some more modest approaches were asking for, well, maybe not as radical as software controls the timing, but at least we should expose the extra architectural state, so the microarchitectural state that's relevant for timing, to software, such that like software can at least react, if not control, but then at least know what's going on, and you can do defensive programming. So if you had, like, this is what we would call a leakage model. So if you have a leakage model of your hardware, it's just like ISA stays the same, hardware stays the same, but at least you expose the information that's required for secure programming. And that's the approach that we're following. Ideally, if you had that, what you could do is you could either like compile against the hardware, if you understand like how to program securely, if you have those leakage models, or you could check whether software is secure. You can also ignore them. If performance is the only thing that you care about, then like you have that information how your CPU leaks, and you just don't care. But if you're writing a crypto system, the situation may be different. And on the other side, you could either check your CPUs, whether they comply with the leakage model, or maybe even future CPUs, you could even design them against the leakage model. So that could be like an additional spec for your CPU that you want to satisfy as a CPU designer. So all of that is good and nice. And here were these like calls for these changes, but not much has happened. And I mean, it's also difficult because there's a whole ecosystem out there. So you can propose radical changes, but good luck with having them materialize. So what I will present to you today is a proposal that I will argue, and I hope I can convince you, that checks all of those boxes. So it's useful from the software side, it's useful for the hardware side, and it's actually surprisingly lightweight and simple. No changes to the ISA are required, and with relatively little effort, we found a way to somehow satisfy those requirements. So let me show you how we do this. And like this, in this talk, I will mostly focus on points 2 and 3. I'll say a little bit about like what you can do on the software side, but topic will be mostly on this part. So first of all, questions so far? No? Okay, so what are those leakage models that we call them speculation contracts? How can you specify the leakage through the microarchitecture of a modern complex x86 CPU, say? So who of you has heard of constant time programming? Okay, most of you. So this notion of constant time programming is actually like our starting point for those contracts. So constant time programming is actually a misnomer. It's a coding discipline, and it's essentially, it tells you how to write your software if you want it to be secure. And what you would do is you would simply make sure that any secrets that you're processing, say a cryptographic key, should not affect the addresses of loads, stores, and branch targets. You should not branch on a secret, and your load address should also not depend on a secret. I mean, if you think about the cache side channel, you know that like addresses of loads leak, so should not depend on secret. Then the idea is you should be safe. The idea is you should be safe is there is actually like, so there's an obligation on software, this is how you should program, but there is an implicit obligation on hardware. And that is, well, we know that addresses of stores, loads, and branch targets leak into shared cache, for example. But the implicit assumption on hardware is that nothing else leaks. If nothing else except these things leak, then actually you can safely, securely run constant time code on that CPU. And this is usually left implicit. And this is exactly what we make explicit. And this is what our speculation contract. But we don't just want to do like a constant time programming. We want to go beyond. We want to model the leakage of modern CPUs with all kinds of speculation. So what we do is we generalize. So what's depicted here in green, so the addresses of load stores and branch targets, we call them observations. This is what an attacker that shares a cache with you could observe. And here, the standard constant time programming model, you would only look at the loads and stores that happen during sequential execution of your program. So what we're doing is we generalize from these observations, and we generalize from the fact, we generalize from sequential execution. We allow richer forms of executions. I'll give you an example in a second. And that allows us to model essentially leakage of modern microarchitectural leakage of modern x86 chips. To give you an example, so speculative store bypass or Spectre v4, like very simple code snippet. Like read that like these instructions from left to right. There's a program. We have two pointers, and they point to the same address. Now, first we load a secret into that address, and then we override that secret with 0. Now we read out the value of that address into a variable z. We dereference that, and now we leak it into the cache. That piece of code, I mean, doesn't need to be meaningful, but that piece of code is constant time because there is no secret dependent control flow, and there is also no load that would depend on a secret. I mean, we store a secret into an address, but then we overwrite it, and here where the dereferencing happens, it's 0. This is constant time code. But on CPUs with speculative store bypass, this is not constant time code. So what happens, we're still X and Y point to the same address, but say the CPU isn't able to determine that. Because say Y lives in memory or is like a complex, computed through a complex expression. So now we write the secret into the address. If the CPU cannot determine that Y and X alias, it can speculatively bypass that store because it speculates that don't alias. And then we read out the secret, which hasn't been overwritten by 0 into Z. Now we dereference that, and now we leak it into the cache. So there's two ways in which you can execute that piece of code. On CPUs with speculative store bypass, one is constant time, the other is not constant time. And the core idea of our speculation contracts is that rather than requiring, like looking only at the loads and stores during sequential in-order execution, we look at the loads and stores on all executions that we can encounter in the CPU. And technically what we do is we essentially say that we always assume the worst case, that the CPU first does this, shows this behavior, then it would roll back, and then it would show that behavior. And we gather all the memory access that can potentially happen, and we analyze our software with respect to that. And in this way, we can model I mean, it's really relatively simple. So I mean, on the modeling side, I'll say something about that later. You would simply say, well, assume that store doesn't happen and see how the program will continue for a bunch of steps. And in this way, we can model many different behaviors. So we have like a framework in which we can express them. And this is always like a combination of first CT, that means like constant time. This is like which observations can you make, and then the postfix here is sec, that means sequential execution. And then we can somehow like we can build like different contracts from different observations and different executions. Doesn't really matter. But so just like the baseline would be just like standard constant time, then constant time with the branch speculation. What we would do is we would just go down potentially mispredicted branches for a bounded number of steps, essentially the depth of the reorder buffer. Look at what's happening there, roll back, go down the correct branch. And well, long story short, I don't want to go into modeling details, but with that simple form of modeling, we can capture essentially all the things that are going on in modern CPUs. Yes, I mean.
Do you assume that, so because most of the time, right, so there are new sources of speculation that you don't know before.
Yes.
Right? So do you assume that you know all these types of speculation before you can model?
Before you can model them,
so
yes.
these contracts. Right?
Yeah.
So does it mean that there needs to be an attack before you can model it?
This is a great question. So in order to model them, we need to have an understanding of not exactly how they're implemented, but we have to have an understanding of what's their effect on leakage. So yes, there needs to be either an attack or you need to have a spec. However, for finding new mechanisms or new ways that speculate, I will show you they would manifest as a violation of that spec. So you say, oh, this CPU satisfies satisfies this constant time contract, and now we have a way to check whether the CPU does it. And any new mechanism that you do not know about would manifest as a violation. Oh no, there's something going on that breaks constant time. So we can discover that, and then once we've discovered it, we can model it. I'll talk about that a little bit later, but it's a great question.
So in an ideal world,
yeah,
would Intel say that my CPU, conforms to these contracts, and then if not, then I'm willing to take my CPUs back?
So with respect to the second part, I'm willing to take my CPUs back. I'm not entirely sure, but I believe that this is indeed the future. I mean, just the same way that you have like a specification of your memory model at some point, as memory models became more complex, is now an inherent part of the ISA. We believe that something like that should and hopefully will be part of future ISAs. It's microarchitecture dependent, so it's not as stable as the ISA. But if you want to write, say, a crypto system or a hypervisor or highly security critical code, you need that information. And you need that information in some processable, actionable form, not like plain text prose that's ambiguous. And I guess this is what I'm arguing in this talk, that so this is, I will show you an executable version of that stuff later. And it's actually, it's a formal spec, but it's not a formal spec that only, the math nerds could understand. It's an executable spec.
I guess, so the thing that, I think it's a step in the right direction. So if you could formally define what the CPU should do, right? But I guess the main value will be if the CPU that we actually buy conforms to it. Right?
Yes. Yeah. So ideally, I mean, right now we're reverse engineering that stuff. Personally, I believe that there will be an advantage for the CPU vendor that first comes up with the CPU that has that contract by design. I think at least security-minded people will appreciate that. Yeah. Then we can discuss like how, I'll talk about that later. Okay. I've given you like the vision. I've given you examples. But give you just like 2 slides for those of you who like math to tell you what is a contract, like formally, like how would you define it? So technically, a contract is just a labeled semantics for the ISA. So the ISA, from a programming language perspective, would be simply like a very simple, this is a simple toy assembly language. It has assignments, has loads, stores, has conditional branches. Let's say that's our ISA. Then what we can do is we can define an operational semantics for a program that's written in the ISA. And that's essentially a way to connect that thing formally to a transition system. So each program defines a transition system, and with those rules, I can tell you exactly what transition system that is. So here is the rule for a load. The state of our program here, this is like memory. This is simply a mapping from addresses to integers. This is the register file. It's a mapping from a finite set of registers to integers. And here we're executing a load. And this rule here says how the state changes if we're executing a load. The memory is unchanged. I'm updating the PC. I'm adding 1 to the PC. So we're going to the next instruction. And we're updating the register X, that's the one where we're loading into, with something that we find in the memory. So very simple. And you do that for each of those instructions. And the labels here, this is the stuff that we write onto the transitions. They say, oh, this is what you actually can observe as a microarchitectural observer when you execute that instruction. So here on a load, you would simply see the address, but not the value of the load. So here we would see this where we're loading from, but not what we're loading. This is essentially it. And this is what I told you, the example speculative store bypass is just like one slightly more complex rule. I don't have a slide for that, but you model it in exactly the same way. So there's just like one rule for the bypass, and then you trace back. It's actually very simple and neat. It's just like 1 or 2 rules for each of these contracts. Okay, and the only thing of like why I'm saying this is because we will just need this notation. So this thing here is if you have a program and that's your contract. So these are like this. These are the observations. This is how these are the executions, and you execute it in a specific state. Then the sequence of observations. So you look at all the transitions that you do, and you collect the labels, and we call that thing the contract trace. This is essentially, if you execute the program with that initial state, then this is the sequence of loads and stores that you're making that we know will be observable, and nothing else. So that object here, I will use for 2 more slides. So 1 slide on software. So those contracts, you get for free a verification or condition on software. And that's again essentially the generalization of this constant time stuff. Make sure your secrets don't affect your contract traces. And what is secret is defined by some relation on states. The formal condition is that a program is non-interferent with respect to a contract, that whenever you run it into initial states that only differ in a secret, then their contract trace will be identical. This is essentially, that's the formal counterpart to do constant time programming. So secrets must not affect addresses of load stores. So secrets, like 2 initial states that differ, say, in your cryptographic key, but the sequence of loads and stores must be identical. And if you have a CPU with speculation, then it's not just the sequence of loads and stores during sequential execution, but also the sequence of loads and stores during all kinds of speculation that you do. So that's the verification condition on software, and people are already doing that. So there's already like an SOK from 2022, like already its first systematization of knowledge with a gazillion of, well, like 50 papers that propose software-facing compilation or analysis techniques. And just for the SOK, people have actually picked up on this contract language because this is like a unifying way. Each of those things, each of those approaches makes different assumptions about like what the CPU does. And here those contracts just serve as a unifying language for all of that. So people are taking care of the software side. The approaches for secure compilation and program analysis. Now, the interesting bit is, but for me, the most interesting bit is, what are we going to do on the hardware side? Because it's nice to make assumptions on your CPU, but we would like to know whether the CPU actually satisfies those assumptions. Okay, and that's what I'm going to talk about now. So now we have those leakage models. How can we actually make sure that the CPU we're running this stuff on actually complies with that model? If it does, well, then we can click guarantees on software together with guarantees on hardware, and everything is nice. Okay, so the verification condition on hardware that corresponds to this constant time thing that I just showed is that a CPU satisfies a contract if programs do not leak more than what is specified in that contract. And technically, that's again some sort of non-interference condition. So for each program and two initial states, if they agree on the contract trace, then whatever, so this hardware, I'll talk about what that is, then whatever you observe on the hardware side in both executions is the same. So essentially that means, think about this, somebody is sitting on, like observe the state of the cache, that could be one instance, then you say like, well, two programs that are constant timed. That's essentially what that says. They should lead to identical states of the hardware after execution. So there's two ways to check whether this. So first of all, does that make sense from a mathematical point of view? It's also hopefully conceivable. So that thing here was on the right-hand side on the software, and it's on the left-hand side on the hardware. So if both are satisfied, you can bring them together, and then your software side guarantees translate to something that works on the hardware side. Now there's two ways to check for this contract satisfaction. So first is you could try to do this via proof. Then you would need to somehow have a mathematical model of what an observer on the hardware side would see. And that's the first thing that we did in 2021. We did proofs for like tiny simplistic models of a CPU. And I think the paper has an appendix of 100 pages of proofs. And whenever I see that, I light a candle for my co-author who did those proofs, because this was a heroic effort and we don't want to ever do this again. People still try, and like for white box CPUs, so like RISC CPUs, there are people who are trying to automate that, and it's like it's a very promising line of work. We did not go for RISC, we went for x86 closed source. The alternative is testing. And to explain what we do for testing, I can actually just use that formula. So what that says is that for every program and every two initial states, whenever they agree on the contract trace, whatever we measure on the hardware must be identical. Imagine like constant time program, like a program that has, yeah, okay. So what we're trying to do is, let's be a little bit more liberal with those all quantifiers. So we can't check all programs, we're testing, we're not proving anything. What we're going to do is we're taking some programs, some randomly generated programs, and we're taking some initial states, randomly generated. And we execute them. It's an operational semantics. It's just like, we just need a simulator. We execute those programs, obtain their contract. Hello. We obtain their contract traces. If they agree on sequences of load stores, then we can actually run those programs on the CPU. We execute those programs on the CPU, measure the final state of the cache after execution. If it disagrees, then we have a contract violation. So essentially, we just turn this formula into a check for an automatic testing tool based on random program, based on random inputs. Yeah.
So I guess the proof one is complete.
Yes.
Right? But the tested one is incomplete.
Yes.
Right? So then my question would be, so because people are trying to do this automatically, these proof parts, right? So for these 5 CPUs,
yes.
My question is, do you think that this is automatable for something as big as an x86 CPU to achieve completeness? Because if not, then Intel will never say that my CPU is, adhering to this contract, right? Because they could not automatically check all the cases, right? And mathematically writing this, I guess, doesn't scale for this CPU.
Well, so I mean, when you do say software verification, right, then there's ways in which you can easily scale. You give up on precision, so you over-approximate. You can still have a proof of safety. You might have false positives, so your checker might say, I cannot determine that this program is safe. I do think that if we want to go down that route, there will be a way to scale verification techniques to larger CPU designs, or to even design CPUs with those contracts in mind. I think why I find this testing approach is very, very appealing is that one thing is like feasibility from a scientific point of view. Can we scale our proofs to these things? Right? The second question is, if you try to do this, you do that for 10 years with your research group, only to realize that maybe the industry doesn't care that much. So right now for us, this is like a way to explore interest and appetite for these leakage models. And if there is an appetite, and we can already we can show that stuff, the usefulness of that stuff via testing. If there is an appetite, then let's think about formal verification. But right now, we can do this relatively quickly and run those the results by our colleagues and by industry partners, see whether they think that's a useful thing to have. And if so, I do think that we can still prove that.
And the question is more like, so where are we going to be 10 years from now? Right? Will we be still in this world where every couple of months there'll be one of these new speculation bugs, or 10 years from now we'll say this is speculation bugs that are a thing of the past. So this is more like the question.
I do hope that in 10 years we can, yes, we can say it's a thing of the past.
Yeah. I also wanted to add another thought that I think if you look at how the testing happens in the architectural right now, it's not either or thing either, right? So if you look at commercial CPUs, they do both verification and random testing. Because with the verification, especially with things like this, you do have to take certain shortcuts, even verification to be able to scale it to large systems. So it would be either verification at the module level, or you do some sort of simplifications in the verification process to scale it up. So it's complementary. So verification still needs certain layers of random testing.
I think from a verification point of view, this is harder than functional verification. And they cannot do already functional verification for the CPUs that they have. Okay. So I think 10 years from now, we will still have these issues, right? So looking at what they are now from a functional verification. So it basically says that we should do testing, which you're going to tell us.
Yes.
And the pragmatic also argument here is that 10 years is nice, but what do we do within the next 10 years as well? So the verification tools, they just don't exist. The testing it's already there, so we might as well.
We have some verification basic tools,
but not for x86. Yeah.
I mean, so the tools are quite generic in terms of system variables.
Well, I mean, you wouldn't be able to verify you wouldn't be able to take one of the results.
We don't know, right? So because we don't have access to this.
Okay, perfect.
Okay. So I've already essentially. I'm a mathematician by training, so I would just explain the whole fuzzer just using this formula, but actually I have a slide here. So this is essentially the architecture of the fuzzer, but there's nothing going on that I haven't explained already. So there's 3 main components. One is a generator component that generates random executable, sandboxes them such that they don't crash. There's a contract component, and that contract component is essentially the executable version of the operational semantics that I've showed you. What it is an instrumented queuing version based on Unicorn, where we simply do stuff like upon a branch, take a checkpoint, go down the mispredicted branch for a bunch of steps, and just like record all the things that we declare as observations, so addresses and roles and stores. And that just outputs, if it gets an executable, executes this executable and records that trace. And then there's the executor that simply takes the executable, runs it on a chip, x86 or ARM. We also have an ARM version. And what it does is it first cleans the microarchitectural state. Slightly more complex than just cleaning, but it makes it deterministic, so we can essentially compare two executions. Execute the test case, and afterwards does a prime and probe attack on the L1D cache and records a bit for each cache set. So it's essentially a 64-bit integer. That's the hardware trace, and it just tells you which cache sets have been touched during the execution of that test case. So example, here's a test case, like a small snippet that Revizor has generated. There's two memory accesses here. First, like the memory accesses are sandboxed, so they all map to one memory page, and we don't crash. Two inputs. So here we have a contract trace. We execute that. None of the inputs we go into this branch, so we only record one memory access here. We execute the same executable on the CPU, and it turns out we will observe two memory accesses. One that agree here on a memory access, like same cache set has been touched, and another one where different cache sets has been touched. And what we actually discovered is that, oh, by the way, this CPU does branch speculation. And in one of the executions, we've entered this branch with two different values of C. So essentially, we've just discovered by automatic testing Spectre V1 gadget. Now, if we don't know what's going on, we still need to do the reverse engineering, understand that this, the reason for this violation is branch misprediction. That's the manual work we still need to put into this. But what we can do is, we can say CPU satisfies constant time, fuzzer says no, and gives you all the speculation gadgets. So this is the test that we're doing. Contract traces agree, but hardware traces don't agree. CPU doesn't satisfy our leakage model. So this is the first testing campaign that we ran. When we published that thing, what we did is we detect V1 and V4 as violations of CTSEC. And now, importantly, when we then say, well, actually, we know that the CPU does speculative store bypass and it does branch prediction. So we model these as contracts, then standard Spectre V1 is not a violation anymore. Right? Then we continue fuzzing, and then we find the next thing. So actually, this is the order in which things go. We say constant time. So it's like, no. After a couple of seconds, you got a Spectre V1 gadget. Then we say, oh, we know Spectre V1 is part of the spec, part of the leakage model. We continue fuzzing, and then it finds Spectre V4 after some time. Then we model Spectre V4, and we continue. And what we did in this first campaign is a proof of concept. We show like automatic detection of Spectre gadget is possible, and we found a bunch of like subtle variants of Spectre V1. So for example, here, if we have a variable latency instruction, and here we have an array access that depends on the result of this instruction, then we actually see that there's a race condition between the duration of this variable latency instruction and the time it takes to resolve this misprediction. So this is an effect that's not modeled in our leakage model. It surfaces as a violation. It's maybe not a big issue. So Intel says like, oh yeah, that's kind of already known by given spectrum mitigations. But it's still interesting that we have like a technical tool that surfaces these things. So we don't need to write a paper about that stuff luckily anymore. So yeah.
So, you know, you mentioned L1D, right? So as a way of
Yes.
observing so whether, you know, there is a violation of the
Yeah.
concept, right? And then, you know, we know that there are other microarchitectural buffers and they leak.
Yes.
And more importantly, these microarchitectural buffers, they work differently across different microarchitectures.
Yes.
Right? So how do you foresee being able to build these observation channels basically over these newer microarchitectures, potentially newer components inside this microarchitecture in an automated way?
Oh, that's a very good question. So, like, right now, the contract holds with respect to a fixed observation channel. So we hardwire L1D as an observation channel, and then we can say, if you decide to say, like, say your Köpf coherence directory is your new observation channel, your contract may look different. So then you would need to do a new fuzzing campaign. When it comes to speculation, I think that all the speculation mechanism will somehow manifest as a Spectre V1 gadget. So this is why we focused on one of them. But I think choice of what is your leakage sink or your observation channel, this is open, and all notions of contract satisfaction hold with respect to one chosen one.
So maybe a related question to this. So do you think then that we need to model different microarchitectural components as part of your contracts, if you want to refine it to also include this new observation channel?
Yes, potentially, yes. And the contract would hold with respect to them. Now, so we're doing, I mean, as we're doing that black box, like L1D is our prime target. If you're a CPU designer, you have very different introspection capabilities. And if you do that at design time, then you can record whatever it is. And as long as it is deterministic, you can apply that approach. So I think that you know, when our hands are tied because we're doing this as a black box approach, but we're showing feasibility. In the future, we hope that people do that at design time, and then, I mean, then you just like trace whatever you want in your, you know, RTL simulation environment, and you get all the information. Yeah.
So you said the word deterministically. So you said that
Yes.
if you can have the observation channel and your data has deterministic behavior. So the question is, for example, in the modern CPU, there are multiple microarchitectural components.
Yeah.
So activated or deactivated based on what other programs are doing, right?
Yes.
A prefetcher is one of them. So
Yes.
the prefetcher might be aggressive or conservative based on what another program is.
Yeah.
So if, for example, the observation channel is the last level cache, or even the L1D, then in some cases, maybe the violations will happen using your model. In some other cases, the violation might not happen, right? Because this depends on the aggressiveness of the prefetcher, for example. So
Yes.
how would you model this, given that the deterministic behavior comes from another program's behavior?
Yeah. Okay, it's a great question. I have a slightly complex answer. I mean, for one, if I don't know exactly how I would model this, but if the aggressive behavior of another program shows up as a violation, right, then I can say, well, this does not satisfy my leakage model because I probably just discovered a new channel through this aggressive prefetcher. In testing, sometimes we try to eliminate this by creating a deterministic testing environment. So we kind of sidestep these effects. So we're eliminating, you know, other cores while we're testing. And how to model concurrent interactions as contracts. This is an open question. I don't have a good answer for that. But I guess if you can observe it, then you do have a
So you play with tuples, so like, so you may have a tuple of models that run
yes,
concurrently, right?
yes.
Then
Yeah.
it becomes extremely complex, basically.
Yes. So yes, yeah. So I like that. There are definitely yes. There's still many research questions. So I think what I'm showing here is like one path where we can make that work. But if you want to face the full complexity of behaviors that you encounter, yeah, there's concurrency is a big.
I give a second opinion on this. With regard to concurrency, so I think the example of prefetchers is somewhat different because there it isn't necessarily strict concurrence. It's more about the microarchitectural state. So whether the type of behavior and type of like the prefetching behavior that you will observe on the system, it's more of a parameter of the microarchitectural state currently, right? So it's not necessarily what happens concurrently with the system, but rather what is the state of the prefetch, right? And in this sense, it becomes more of a question of coverage rate. So if we want to detect this kind of violations and we want eventually model them as well, we just need to find the speed in the given state, like with the given microarchitectural state when we start executing the test case. And it doesn't necessarily matter what happens concurrently. So there are still some classes of issues where concurrency would matter. I still agree with you. So that would be coherency protocols and such. There you like actually need concurrency, not necessarily microarchitectural state. But at least like I think many of these complicated cases would be just boil down to having the program run in a given microarchitectural state.
Yeah. So when I talk about prefetching, based on the microarchitectural state, I'm saying that another program triggers the prefetcher because of bandwidth consumption or another metric, right? So I'm not saying that the prefetcher is working in a deterministic manner. I'm saying that another program is triggering the prefetcher. A concurrent program is triggering the aggressiveness of the prefetcher at the last level cache, for example.
Can I maybe a related kind of question? So how complete are programs that you generate for testing?
There's no notion of completeness. I mean, we can describe completeness in terms of the fraction of the ISA that we're covering, for example. But that's about it.
So currently the structure is just like has branches and control. Is it one control flow? Is it two control flow? Is it 10 control flow?
You can configure the number of basic blocks that you would like to have in your program. You can configure the which parts of the ISA you would like to have. You can configure probability of those different instructions being inserted.
So, and then you generate these programs like based on this, and then these are valid control flows, I imagine.
Well, there are, yes. So I mean, like for the basic blocks, we wire them to be valid control flows, and for example, for memory accesses and say division operations, we instrument them either to produce faults if desired. I'll come to that later, or not produce faults if desired.
Do you also play with the dependency chain, for example, when making branches or different types of branches?
I'll talk about that in a limited way, yes. Very quickly, everybody. So usually I'm mindful of time, so I'll try to finish by the hour. Then people can leave or stay for discussion afterwards, if that's fine with you. So I have another hour. We can then go offline and discuss more technical details. But let me just finish the talk in 5 minutes, and then we can. So I'll just quickly talk about 2 more things. So this was like the feasibility study. Oh yeah, we can detect Spectre everyone. Great. So conceptually, it's great because now we can do it automatically. But in terms of what we found, nah. Like we show that to our security response team, and they say like, oh, nice, but not that exciting. So we did 2 pieces of work to there's more ongoing, but 2 published pieces of work to get to a point where people care. One is increasing speed. First, like only a very small fraction of the test cases that we're considering are actually interesting. Only 13% misspeculate, and only in those we can actually hope to see any transient execution leaks. Only 7% of those actually do memory accesses that would affect the cache. And then because we're trying to generate inputs that match on the contract trace, only 6% of the inputs actually collide. They don't collide, and so only like 0.5% of the entirety of test cases are actually like promising candidates to surface anything interesting. So what we did, that's from last year's Oakland, very quickly explained 3 optimization techniques that each targets one of those bottlenecks. One is, before we do the expensive analysis on the contract, we run the test case on bare metal and use performance counters to see whether it's actually speculating. So we're simply comparing the number of issued and retired instructions. If it's the same, there's nothing interesting going on, throw away the test case. So we just like execute it quickly on bare metal before we do any expensive analysis. Second is, if a test case speculates, we just like add fences after every instruction and see whether the final cache state of this fence version and the non-fenced version coincide. If they do coincide, then the serialized test case does exactly the same memory accesses, so the test case is uninteresting. Throw it away. That's, by the way, like very similar to a technique that folks at the Project Zero used to find the Zen bleed. And finally, rather than hoping for collisions on the contract trace, we use a taint tracking approach to just generate inputs such that we know that they produce the same contract trace. All of that combined gives us speed ups, detection speeds of like a couple of orders of magnitude more for known leaks, and it also allows us to go much deeper in our fuzzing campaign and discover new leaks. So first time, like 2 entirely undocumented forms of speculations we found. So one is string operations speculate, and then there's a strange way in which division on 64-bit operands speculates. Not documented before, but okay, like new proof of concept, like, okay, we can actually find new stuff. We go to Intel, we go to AMD, and this is like, well, okay, it's not a real security issue here. So again, it's a great step forward, but nothing earth-shattering from a security point of view. Okay. And then the latest piece is we extended the tool to cover CPU exceptions because, I mean, first, it's a very important for many virtualization relies on exceptions. So, and many microarchitectural attacks are actually exception related, like LDI, Meltdown, MDS. So the most impactful attacks are somehow related to exceptions. But there's no leakage models at all so far. So like everybody in the PL community, like those 50 papers that I showed you, they all look at different kinds of like V1 or, you know, the store bypass, but like nobody goes. There's not even an attempt to model leakage on exceptions. So this is why we were faced with like, how do we even start? I think this is the answer to your first question. So what we actually do, and I think this is, I really like that approach. We start with the very strict model. We say constant time. And then we test against hardware, like completely unexpected, we find a violation. Now we look at that violation, we model this, add this into a model that's slightly more permissive. Then we continue testing until we find the next violation. And here we really do it systematically to infer a leakage model because we have no clue. And we just do this until we converge. So now we have like a leakage model, and we did that for AMD and Intel CPUs, leakage model for exceptions that we can now fuzz for days and we don't find anything new. So it's not no complete coverage, but it's these are the best leakage models that exist, and we found them in this iterative manner. So here's a family of leakage models like that we proposed. I'll not go into the details of those in the interest of time, but they're actually like pretty cool. Increasingly weaker forms of leakage, and then we ran a testing campaign So these here are the leakage models. These here are different forms of exceptions, including memory errors, division errors, and opcode-based errors. And we do this, so these are the leakage models, like from this here is constant time, and then increasingly more permissive. And we ran it on 4 different Intel and AMD CPUs. And each experiment ran for 24 hours or until we found a violation. After 24 hours, we time out. So we start from left to right, as I described. So here we're just like violating. So here AMD satisfies the first leakage model. So this is simply, it's simply delay handling of essentially just out of order execution, but nothing major. Here we find that there's actually like a no value injection. And here we find like that in one case, an Intel CPU satisfies the weakest of all contracts. So this is how we go from left to right and determine what's going on. And so we did that for the whole table. We found essentially all known forms of exception leaks that have been documented in the literature that like fall into the scope of what we support. And we also find 3 entirely new leaks. And this one is the first one where like we can argue that well, it's a security issue, and that is that the divider state on Zen plus persists. So if you do a division by 0, what the division unit will return is actually the value of the previous division that you did. You do a division by 0, and that state persists even across process boundaries. So you can essentially leak across security domains. You just like trigger exception, you do a division by 0, and you know what the previous process actually was computing on. So yeah, so that resulted in some fixes in the Linux kernel and also in Windows. And we discovered it exactly in the way that I described. So, which brings me to the end. To summarize, so specifying and testing microarchitectural leakage is actually feasible and surprisingly simple. And I'm saying surprisingly simple because, I mean, literally, this is the result of like a project that started in our team 3 years ago. We showed how to specify leakage. We showed with Revizor how to test against leakage, and now we just increase the scope and robustness of the tool. It's not that we did that for 20 years and we still run around with the same story. So that all of that happened in 3 years. So we're reasonably optimistic that if we continue on that trajectory, then we can actually achieve something. So there's many avenues for future work, including design time analysis and many more things. These are the papers. Revizor is open source. It's robust. It's beautiful. Thanks to Alexei. Download it, take a look, play around, find your own Spectres. We have a whole project at Azure Research where we're looking at the side channel attacks, not only Revizor, but also like at the cloud scale. How can we isolate virtual machines, confidential virtual machines? There's some exciting work upcoming. And then we do have open positions for postdocs in case anybody is graduating and interested in that stuff. And now, well, thank you very much for attending this one. Ready to take questions.
So maybe we can stop our stream and just get into discussion.
Sounds good.
Okay. Just give me a second.